Hello again, this is Galen Pickett, Cal State Long Beach, Physics 151. Now I want to talk about Chapter 4, Section 10. So this is what does the momentum principle look like when delta t becomes very, very small. And if delta t is very, very small, then R initial and R final will be very, very close to each other. P final, P initial will be very, very close to each other. And the update forms are not the most convenient forms for both position update and momentum principle update to understand what's going on. So here you can see what's going to happen here. If I make the delta t get smaller, so if it was 1/2 as big, then the R final would be, instead of where I drew it, it would be right there, halfway in between. If I made the delta t 1/10 as big, the R final would be right there. If I made it 1/100th as big, it'd be sitting right there on top of the R initial, and it'd be very hard to tell what's going on. Same thing for P initial and P final. If delta t is very, very small, then the momentum will hardly have changed at all from one instant to the next. So instead of writing final and initial, I'm going to write the momentum as a function of time. It's a vector function of time, but it is a function of time nonetheless. It is the momentum at the final time, which is the initial time plus some very small time I'm going to call delta t. Eventually I'll take the limit as delta t goes to 0. And that's still equal to the momentum at the initial time, which is just t is equal to t initial, plus delta t times whatever force is being applied to the system during that time, delta t. Now I'm going to subtract the momentum over to here, so I've got p at t initial plus delta t minus p at t initial is equal to delta t times the force. And let's say that that's the force at t initial. We're just going to assume that the force won't change during this time delta t. Now if I let delta t go to 0, this side goes to 0 and that side goes to 0. So there is a force, but it has no time to act, so the momentum doesn't change. So taking the limit delta t goes to 0 gives me 0 is equal to 0, which is what it should give. So that's a good skeptic review, but it doesn't help me analyze the motion. I'm going to divide both sides of this by delta t. So I've got p t initial plus delta t minus p at t initial divided by delta t is equal to force and now t initial. So here I've got the p final and the p initial are going to be very close to each other. That is going to be very, very small, but the delta t is also small. So I've got now, when I take the limit as delta t goes to 0, I've got 0 divided by 0, and I'd have to use L'Hopital's rule to figure out exactly what that limit is. In this case, that is a limit. So when I take the limit as delta t goes to 0, you can see this is a difference quotient that I'm taking the limit of. It's really just the definition of the derivative. The time derivative of the momentum is equal to the force from the surroundings. And this is the infinitesimal time form of the momentum principle. Now there's one more thing we can do. There's an assumption we can make. We can assume m of t is some constant. Now we usually make that assumption. I'm talking about a baseball, its mass doesn't change while it is being thrown. But if the mass is a constant, then I can write this master form of the momentum principle as d by dt, some constant times v of t is equal to the force. Now if I take a derivative, I've got a constant doesn't depend on time. I could write this as m0 times d by dt v is equal to the force from the surroundings. And this quantity here, the rate at which the velocity vector is changing, that has a name. That is m0 times the acceleration is equal to f. And this is the way Newton wrote his second law of motion. F is equal to ma. And if you've taken a physics course before, that's the way you know the momentum principle. But it's really just a consequence of the true momentum principle with one assumption. So this second law of motion is really something that is derived from the much more fundamental and important overall momentum principle.